Let's rejoin our conversation with Professor Geoff Sutcliffe for this final part 3 of our interview. What do you think are the most exciting developments that are coming in ATP, especially things that you're just working on, just starting, or that you're seeing emerging?
And so I think there are two things coming up, both of which relate to the application of ATP theorem proving to the real world. One of which I've already mentioned a little bit is this interest in reasoning about law and ethics, and let's say medical data, privacy, using and getting that right. And in order to do that, because these issues in law and ethics are often have contradictory backgrounds or very subtle aspects, you can't use classical logics to do that. And I think there's a need to do, I think there will be a development of firstly the non-classical logics, starting with good old-fashioned modal logics, where things are necessarily true or possibly true, deontic logics, where things ought to be true or think it's permissible for something to happen, and going through conditional logics and public announcement logics and dynamic logics, which give you a more subtle language for describing the known facts and the things you want to prove. And this work is going on, and it's become more possible thanks to the work of Chris Bensmuller in Berlin, who's found a way to take these non-classical logical ideas written by lawyers or medical personnel or doctors and translate them into a classical world and do the reasoning in the classical world. And then still open research is to take the classical results and get the description back into the language of the doctor, lawyer, ethicist, or something like that. So working with the modal logics is developing, and that's something I'm working on. In fact, was working on half an hour ago before we started talking, building some infrastructure for that. Related to that, and again, I've mentioned this, there's a need to have logics which have more than two truth values. Things are not just true or false. And there's the whole realm of fuzzy logics, multi-valued logics, and related topics. How do you reason across those? Probabilistic reasoning. Work was done, Max Planck Institute in Saarbrücken a lot on this, and they gave up because it's difficult. And again, that's research areas. Certainly multi-valued logics is something I have an interest in. I've been working in four-valued logics where things are true or false, both true and false, or neither true nor false. And I'm working next on a six-valued logic that takes those four plus two other truth values, more true than false and more false than true, but not completely true and not completely false. And how do you reason across those logics? And having modalities and multi-values gives you a lot of subtlety for describing the world. The next topic, which really hasn't been addressed, I did a little work on this in 2008, is dynamic data. So the way that automated theorem proving works now, it assumes that your set of known facts is unchanging. Of course, the world is changing. If I wanted to write an automated theorem program to do some stock market analysis and tell me when to buy or sell, every second or millisecond, the prices of stocks change, and you can get this data off tickers, no problem. So how do you you've got an axiom, a known fact that says the price of Apple is whatever it is today, 200 and something. But, and it's going to move, and you want to have that fact changing during the reasoning process. So dynamic real-time data being integrated into automated theorem proving is a challenge that needs to be addressed in order to reason about real-world situations. There's so many examples. If you've got the reasoning thing in your airbag chip that I mentioned, well, it's got a piece of data which is the current speed of the car, and it knows what to do. Well, that speed is changing as the person accelerates or brakes. And so you need to have that data changing continuously, and the reasoning process updating its conclusions, what it derives from these facts, being reactive to the changing data that underlies it. And that's something I'm really interested in doing. And if I could fund a PhD student to do that, again, remember, donations at www.tptp.org. I think that there's a really an open territory down there to work on that, and that would be very interesting. So those are two things. And I would say support for the integration of machine learning and theorem proving is something that's of interest and development of that area. But I've spoken a lot about that already.
Yeah. Yeah, great set of topics. And I really like that you mentioned Chris Bensmueller's work, since he and I have done a little bit of stuff together. And it seems to me that his work provides a bit of an answer to those folks that would like to say sort of that all facts are sort of partially true. I've certainly had that challenge presented to me. How can we work in logic when so many things are, and maybe the strong assertion is that everything is somewhat in doubt. And I think he's shown at least there is an approach with these higher order logics, using modal logic inside a higher order logic framework, that you can say things like it ought to be true, it should be true, it's mostly true, but still be in a sort of true false world, but capturing these sort of wrappers around truth about what the truth means. As a way to model the world, which seems to me to be very, very reasonable and also very exciting. And so when people are talking about having to use a certain representation, like a probabilistic representation, well, that's one perspective on it. But another perspective is that we capture what we mean by true in a certain case. We provide a wrapper for it that explains what that truth means relative to everything else.
Yeah, that's Bensmueller's technique, is to think of modal logics and multi-value logics as a wrapper around classical many-type higher order logics, and translate from the wrapper down, do the reasoning with the machine inside, and then translate the results outwards. But at this stage, Chris doesn't have the technology to translate the results outwards yet. So that's another nice research topic. And if he gets himself a good permanent position. There's also Alexander Steen at the University of Luxembourg with Leon van der Tor. Leon van der Tor is very much involved in ethics, capturing ethics, and Thomas Leibel at the American University of Paris. And we have to have this interaction with people who understand what ethics are in some sort of formal way, or what laws are in some formal way, who can then interact with people like Bensmueller and myself, who sort of come down into the classical core and then sort of bubble it back out again in the future.
Yeah, another one of the challenges of research communities is working on a topic like getting high performance theorem proving isn't necessarily focused on the representation itself, but rather, given a representation, how do I do things that are fast?
Yeah, right. Sure. You don't want the computer program in your airbag, you don't want it to go off slowly.
Yes.
The bag's got to go off now. No questions. You can't wait 30 seconds and it says, oh, I think I should deploy the airbag as you impaled on your steering wheel.
Right. So we should also spend a little time talking about really, I think if somebody looks at your research output over the years, one of the first things that they're going to see and be aware of is all of your work on the TPTP framework, the language, the way that it's brought all the community together in practice, the theorem proving competition, the library. Can you just give a little orientation for our viewers on that research and its practical impact on the theorem proving community?
Okay, so I can go historically. This project started in 1992 with Christian Suttner at the Technical University of Munich. And the original goal was to provide a set of test cases to help people who were writing automated theorem proving programs, writing the software, we were going to give them test cases to test their theorem provers and make sure that they were doing the right, getting the right results. And if they couldn't, here were some challenges they could work towards and improve their software. Over time, the project's expanded. It's sort of like a child. I mean, if you think 92 to here we are, this is almost, how old is my baby now? It's 29. I've been working on the same project. And what it really evolved into for me was thinking about how do you deploy automated theorem proving software in real applications for users. And users, be they mathematicians or geographers or biologists, don't want to think about the geek stuff that's going on in these computer programs. They're very complex computer programs, and in a sense, quite difficult to use. They're not user-friendly. So I think somewhere at the top, they're the users who want to do something, and somewhere at the bottom, there's geeks who want to sort of who can provide reasoning. And there's this middle layer, and I've filled in that middle layer for the classical logics through the TPTP project. I should mention, to be fair, the SMT-lib people have also filled that middle layer, but they are particularly focused on users who come from hardware and software design through to people who can verify that sort of thing. So they have a specific niche, it's a slice of the pie, and boy, they're good at it. They do that well. I have a broader range of application in the TPTP project. So continuing on through the history, over the years, we started TPTP with very simple classical logics. And over the years, I've been adding on other new logics, going to full first order, typed first order logic, polymorphic logics, higher order logics. That was work with Chris Bensmuller, who we've mentioned, polymorphic higher order logics. And right now I'm adding on extended first order logics. And I hope by the end of my sabbatical, I'll have the modal logic strapped on the side to this as well. And it provides as a project three things probably. One, a set of test cases that I get from these users. They tell me their stuff. I encode it or help them encode it into one of the TPTP languages, the few that I've mentioned, and hand those off to the people at the bottom who write the theorem provers and say, here's the challenges from your real users. Now you've got to develop your software in order to cope with these challenges that trickle down. And that's sort of one aspect of it. Another aspect of it is having got these challenges and the theorem proving guys at the bottom do their thing, I capture the output from their theorem provers and store those away in a database. So it allows people to look at how problems have been solved, what techniques work well in the automated theorem proving community. And that's the strap-on project called the TSTP, Thousands of Solutions for Theorem Provers. The TPTP is thousands of problems for theorem provers. So I work those two things continuously together. And then, as you mentioned, one of the fun parts of it, and it's, let's be honest, it's less scientific than the other parts of it, is the theorem proving competition that I run each year in the summer, where we take the theorem proving programs from the people at the bottom and we give them a set of challenges with limited time in order to solve them and see who can solve the most problems, within a 6-hour time window or something like that. One of the great things about the competition is that, as well as being a real evaluation of the quality of these programs that are competing down the bottom, it also provides an environment for people to interact. And it's the people at the bottom, the people at the middle, and the people at the top. Because we have t-shirts, we have gambling, we have a big dinner together, and everybody talks to each other, and it provides a very inspiring environment. It's useful for people at the top to understand what people at the bottom are doing and vice versa. And it's very useful for students who come in and they're new to the whole game, and they can sit down at the dinner table with a bottle of red wine and Stefan Schultz or Andrei Voronkov or Giles Rieger and really learn a lot, much more than you get from reading their scientific papers published in prestigious journals. You can get a lot more over the dinner table than in some ways than you can from sort of real scientific research, although of course both are valuable. So that's been one of the fun parts, and I'm a little bit known for running that competition because we do have a lot of fun interacting and talking. And then the evaluations have a downstream impact, particularly for the people at the bottom, because if they perform well there, then people at the top say, oh, well, I'm going to use your tool because it performs well in the particular environment that I'm trying to reason about. So those are the three main sort of aspects of the TPTP project. And I hope it will keep going for some more years to come as I keep on adding more things. As I said, multi-valued logics, modal logics, non-classical logics, and extended first-order logics are in my next few months of effort.
Yeah, I think it's been a tremendous resource to the community on so many levels. So in this notion of having a competition, a friendly competition that allows people to see how their work is doing. I mean, somebody developing a new theorem prover might think that they have something really great and on a small problem set, but when tested against the, I guess, almost 25,000 problems in the TPTP, you get a really broad view of what works and what doesn't, and a comparison to other people's work. And it allows this sort of objective sense of performance in a way that certainly wasn't possible before you started this. Before you started this, I mean, people might be working in first order logic, but they might have a completely different syntax, maybe some different extensions, and really no way to say that they had a good result other than on a very small, very local or parochial set of problems or tests.
Yeah, there's two sort of subtle aspects to that. One, which we recognized right back in the early 90s, people would write their new theorem proving program and they'd test it, and they would test it on a set of problems that really worked well for them because they'd sort of cheat it a little bit. And they'd say, look, my program is fantastic. It can solve all these 10 problems, and publish it. And Journal of Automated Reasoning have examples of this. But we saw a flip side to that. We saw people doing excellent work and testing it on the wrong set of examples and getting discouraged and say, oh, my program can't do anything because they tested it on inappropriate test problems. And that was one of the things we said. You must find your niche. And there are particular theorem proving programs around these days. If we take, for example, the iProver program of Kostyakorovan, it's not good in general. It's good, but it's not as good as the leaders in general. But down in the effectively propositional logic, which is a slice of the logic pie, he's fantastic. And so it wouldn't be fair to evaluate him on the broad spectrum, but to evaluate him on what he's designed to do. And that's been a useful thing, because the problems in the TPTP are divided up into different types. And so if you're developing a theorem prover, you can target a particular characteristic of problem. You say, these are the types of problems I want to answer. For example, for this effectively propositional logic, Intel, who designed chips in Israel, turned out that to verify their chip designs, the problems that came out in logic were in this category of effectively propositional logic. And they didn't care for the E and Vampire, the big players. They used, in fact, Kostyakorovan's iProver to verify their chip designs because it was specialized to this particular slice of the logic pie.
Yeah, it's great. Both you've got the evaluation for what we might call the specialized provers, and then also a broader evaluation overall, so that the users can be informed about which prover they're picking and why. Also, we should mention maybe the work that you did with Aaron Stump on the Star Exec platform, because testing your stuff on 25,000 problems is pretty computationally challenging. And so for these developers, and now in myself included, in a little project I've been doing with Stefan Schultz to write our own simple prover so that I can learn about how ATP is done, and hopefully we'll be able to publicize this a bit more so that more people can come into the community and see that it is feasible to write your own and really understand some of the guts of a prover. We were able to test it on your Star Exec platform in a way that really wouldn't have been possible if I just had a server at home.
Yeah, Star Exec's a nice project, and kudos to Aaron Stump and Cesare Cinelli, who had the idea at first. As you've mentioned, as these libraries, the TPTP and also the SMT library, which runs out of Cesare Cinelli's group, as they grew with large numbers of test problems, it turned out you can't do enough testing on your laptop, and people are starting to use their student labs and run it across the 30 computers in the lab or buying hardware. And Aaron and Cesare saw the need to provide a centralized resource focused on providing the facilities needed to test automated theorem proving programs over a large suite of test data. And so, wow, I'm trying to think, this is probably 8 years ago, maybe more now. We put a grant in, and thank you to the American taxpayer, the NSF gave us almost $2 million, and we installed a large number of computers at the University of Iowa and built a software framework called Star Exec, which enables people to upload their theorem prover and upload their test problems, or use existing test problems uploaded by myself, for example, in order to evaluate what was going to test their theorem prover, find out what they could solve, what they can't solve within given resource limits. And that turned out to had more impact than I sort of imagined it would at first, because it was really adopted by a large fragment of the theorem proving community for testing and developing. Additionally, we've used the platform, the Star Exec platform, for running competitions. The competition that I run, which has been going on for since 1996, I think. 23 or 24 editions of it, but more competitions have come out of the woodwork since then, as it became evident that competitions were a good way to foster development. And we started running competitions on the Iowa platform, and the Iowa platform started getting overloaded. So thanks to the American taxpayer again, we got a second grant, which enabled us to increase the compute power in Iowa and to build a second installation of StarResec here at the University of Miami. And the one at the University of Miami is focused on the TPTP community. It's not as big as the Iowa group. And the Iowa one, I think now has 200 quad-core computers, 192 of them. And I've got 32 octa-cores here. And you can have an account. It's free to anybody who's doing anything reasonable for testing your theorem prover and doing evaluations. And you can get at the data and provide your results for your publications or to prove to your boss that you've really done a good piece of work.
Yeah, fantastic. You've really sort of created the AWS of theorem proving, and it's a tremendous resource.
Yeah, it is. Well, it is. It's been more successful than I thought it would be. People are just, I mean, I look at the compute load in Iowa and here, and the compute load is always, the machines are flat out. We're making heat in the machine room.
Yeah. Well, this is maybe this is a good place to kind of wrap up. I mean, we've talked about so many things connected with theorem proving, the research itself, all of the partnerships, the research that you've done with others. And I think that the arc of your career is really remarkable in that you've done both a tremendous amount of individual work, individual research, enabling research that other people have built on, but also the sort of community building part of science that you've done, creating this competition, creating common platforms and frameworks for others to build on. You've really brought together and enabled a whole community to do research that really has become greater than the sum of its parts. So our conversations are always exciting. I look forward to more. I look forward to continuing to work with you as part of Articulate Software and seeing all the great things that come out of your lab at University of Miami. So thank you for spending all this time talking about ATP and your research.
Yeah, thanks, Adam. And to finish, maybe I could give a quick plug in the opposite direction. Back somewhere in the 90s, was it, when I first met you, Adam, you had the SUMO, Suggested Upper Merged Ontology, which was the first large theorem proving problems we had come across. Our cooperation trying to do theorem proving over SUMO really led to the current area of large theorem proving, this big problem of selecting which known facts to use. And I remember a workshop, possibly at Jacobs University in Bremen, was it, where we had the first workshop on empirically successful reasoning and large theories. And if it wasn't for SUMO, that whole area would not have actually happened. And it turned out to be important for many, many users now. So kudos to you for making that happen, because I know that was a large piece of your life that must have been carved out as you learned about weapons of mass destruction and many, many other topics.
Yeah, and thank goodness it's continued. So we'll look forward to doing a lot more work together on large problems like SUMO and delivering high performance results in theorem proving and reasoning to a lot more people in the future. So thanks again for doing this, and looking forward to more talks together in the future. Thank you.
All right. Thanks, Adam. Nice chatting.
All right. Take care. Bye-bye.
Bye.